Okay, let's get started. Today I want to finish up the conditions of equilibrium as we know them in thermodynamics and move into the thermodynamics of a very simple solid. We begin with the fundamental equation, which is an equation that contains within it all of the thermodynamic information you could possibly know about a system. This, incidentally, if you've had any exposure to statistical thermodynamics, is the sort of thing that you calculate in statistical thermodynamics from what they call partition functions. For an isolated system, the controlled variables, if we're talking about some kind of fluid, in that isolated system, are the energy, the volume, and the chemical content, because these are the things that we put into the system before we isolate it, so we know what they are. The system will then evolve so that it has the highest entropy consistent with these values of these quantities. The relation between the entropy and the quantities is the fundamental equation. And it contains all of the thermodynamic information in the sense that if I take the partial derivatives of this function, the partial of S with respect to E is the reciprocal temperature, the partial of S with respect to V is the pressure over the temperature, the partial of S with respect to the mole number of a component is the chemical potential, or negative of the chemical potential divided by the temperature. So by differentiating this equation, once I know what it is, I get all the thermodynamic forces. Furthermore, if I won't go into it now, but if I take the second and higher derivatives, I get the various thermodynamic properties, like the specific heat and the compressibility and things like that. It's all contained in this one equation. That's why we call it the fundamental equation. However, the entropy function is not a convenient one to use, so we generally turn that function around and use the energy function or some modification of that. Energy is a function of entropy, the volume, and the chemical content. It's nice to think of this as being the governing function for some system in which we control these variables. Well, I'll get back to that in just a moment. In this function, the first derivatives give us the temperature, the pressure, and the chemical potentials. The second and higher derivative give us the specific heat, compressibility, coefficient of thermal expansion, and so on. The conditions of equilibrium and stability, if we can express them in terms of either the entropy or the energy. If we consider the entropy in a system that has given values of E, V, and N, then the entropy must be a maximum. Therefore, any change that we might make in the system would cause the entropy to go down. So we look at a system, we consider the state that it's in, we say, can we test to see if it's in equilibrium? Well, the first test would be to make whatever infinitesimal change we could make, holding the energy, the volume, and the chemical content constant. That is, these are changes we could make in the internal state of an isolated system, because these quantities are fixed. Well, if the entropy has an extremal value, then those changes must all lead to entropy changes that are less than or equal to zero. That's a necessary condition of equilibrium. If that equilibrium is going to be stable, that is, if this entropy is going to be a local maximum, then a larger change, the second derivative if you want to, the second variation of the entropy, has also got to lead to a decrease in the entropy. And in fact, a sufficient condition for stable equilibrium, these conditions of equilibrium and stability are satisfied by a local maximum in the entropy, a state which is metastable, but maybe not fully stable. A sufficient condition for stable equilibrium that no further change is possible is if we make any finite change in the state and we reach a true maximum in the entropy, something up here. Well, now I can flip those around and express them in terms of the energy. And in fact, this is the kind of the function that you have intuitively been taught over the years, and going all the way back to perhaps as long as you consider the stability of systems at all. The condition on the energy is that for given values of entropy, volume, and chemical content, the energy must be a minimum. You always think naturally of equilibrium being the state of lowest energy. Well, now how can that be? Because this minimum energy condition refers to a situation in which we control the volume, chemical content, that's easy, but we also control the entropy. Now how would we do that? Well, if you think of the situations in which you've been told the energy is a minimum, it's like a ball rolling down a hill or other situations that involve situations in which thermal contributions are not important. We won't talk about it much in this course because we don't need to, but there is a law of thermodynamics, the third law of thermodynamics, that says that when we go to the zero of temperature and the low temperature limit, the entropy vanishes. The entropy of the equilibrium state at low temperature is zero. Well, if the entropy vanishes at low temperature, then the entropy is controlled because it isn't there. So when you've been told, as you were in many courses I'm sure, that systems seek a situation that has minimum energy, what they're really talking about is situations in which we have very low temperature or virtually no degeneracy, like a ball rolling down a hill, so that the entropy is controllable because it's effectively zero, where thermal phenomena are not important. When thermal phenomena are not important, the entropy is irrelevant, and then the condition of equilibrium is that the energy be as small as possible and have a minimum value. Well, the necessary conditions of equilibrium, we next look to the internal equilibrium. We did this last time and asked, what can we say, what conditions must pertain if a system is to be internally in equilibrium? And last time we considered various, what we actually did was we took a small element of a large isolated system and said, let's consider redistributions of energy, volume, or chemical content that might occur within that small element, and ask what conditions must be satisfied so that none of those redistributions can cause a decrease in the entropy. The conclusion we came to are the internal conditions, the necessary conditions for internal equilibrium. In order for this little element inside the material to be at equilibrium with respect to redistributions of energy or volume or chemical content, we must have the temperature constant, the pressure must be constant, and finally the chemical potential of each component must be constant. We got something else too. If we have a temperature gradient, that is, if we have two adjacent regions that have different temperature, the result will be equilibrium will be approached by heat being transferred from the high temperature region to the low temperature region, consequence of the second law. If we have two different regions that have different pressure, the mechanical change will be to expand the high pressure region at the expense of the low pressure region. So that's the direction mechanical change will occur. And finally, chemical equilibrium, if we have two regions that have different chemical potential, we will get a spontaneous redistribution of material from the region where the chemical potential is high to where it is lower. Now I said just as an asterisk that these conditions, the chemical and mechanical conditions of equilibrium, change just a little bit if we have to take gravity or other external fields into account. We don't normally for our purposes, so we can forget about that sophistication. The next thing, however, we need to be concerned about are conditions of global equilibrium. And we've actually already written two conditions of global equilibrium. If we have an isolated system, our condition of global equilibrium is that the entropy be a maximum. If we have a system in which the entropy is unimportant, the condition of global equilibrium is that the energy be a minimum. But in fact, in most of the experimental situations in which we find ourselves, let me correct that, we can take any system and make it an isolated system by including everything that interacts with it. But that's rather inconvenient. You know, if you walk into a laboratory and you start heating up a sample, you don't really want to have to include the Bunsen burner or whatever it is in your description of the system. You don't care about the darn thing. It's just or the furnace. It's just a device to control temperature. If you put something in a tinsel machine and pull on it, you don't have to include the machine in your analysis. At least most of the time you don't. So we need a way to consider, to write the conditions of equilibrium for systems in which we are not isolated, and entropy is important, but other things are controlled, such as the temperature or the pressure or the chemical potentials, because these are the experimental situations with which we ordinarily deal in the laboratory. So we want a way to rephrase the conditions of equilibrium so that we can consider a system, for example, that has its temperature fixed without worrying about the thermodynamics of the device that's fixing the temperature. And that leads us to the other conditions of equilibrium. Well, here's just the energy and entropy again. Oops, because I repeated all the slides. In fact, we will consider three cases. These are the common ones in thermodynamics. First of all, consider when a material interacts thermally with its environment, but thermally only. Imagine a situation in which the things that we control are the temperature, the volume, and the chemical content. We have something that's in a furnace, sealed inside some fixed volume with a definite chemical content, but it's in a furnace, and the furnace is fixing its temperature. In that case, it turns out that the condition of equilibrium is governed by what we call the Helmholtz free energy. F equals E minus T times S must be a minimum. If we consider a system that interacts both thermally and mechanically with its environment, take something that is has a sealed surface, but has a piston that can deform it mechanically and it can conduct heat across its wall, that sort of thing, it turns out that Gibbs free energy is the relevant parameter. G is E minus Ts plus PV. Finally, if we consider a system that's open, just take some of the air in this room and close it with an imaginary boundary. Well, in that case, we control the volume because we've drawn our imaginary boundary, but the temperature is fixed by the environment, and the chemical potentials are fixed by the environment because material can come in and out. In that case, the thing that turns out to be the proper potential is what we call the work function, E minus Ts minus the sum of mu n. Let me show you that these things I just said are true and why they're true. Suppose that we consider first a big system which is isolated, but we're not interested in the big system. We're only interested in a subpart of that big system, which is surrounded by a fixed wall that fixes impermeable wall, which fixes its volume and chemical content, but allows energy to pass back and forth. Well, if this system is small compared to its surroundings, then the energy that falls back and forth will not perturb this surrounding, which calls a reservoir in any measurable way. The temperature of the reservoir, by the conditions of equilibrium with this energy equilibrium, will fix the temperature of the system. So if I have something that looks like this, the variables that I can control, the things that I can manipulate, are the volume, because I set this boundary, the chemical content, because I put chemistry into this volume before I sealed it off, and the temperature, because I can control the temperature of this reservoir, this furnace, this big thing that has a dial that tells me what the temperature of the system is going to be. If I consider the system and the reservoir together, I have an isolated system. And my condition of equilibrium is that if I make any change in the state of the total isolated system, then the total change in entropy, which is the entropy of the system, I'll leave no subscript, plus the entropy of the reservoir must be less than or equal to 0. Well, let's take a look at that. Delta S total must be less than or equal to 0, equal delta S plus delta SR. Well, the entropy of the reservoir, the only changes in the reservoir we care about are changes that are brought about by exchanges of energy with the system. We don't care what happens to the reservoir internally. In fact, we don't even care what it looks like. All it's doing is setting the temperature and exchanging energy with our system. So the change in the reservoir that matters to us, the change in the entropy, is 1 over T, the change in the entropy of the reservoir. Energy is conserved, so this is minus the change in the energy of the system divided by temperature. So let's take that, plug it in for del SR. Temperature is a positive definite number, so we can multiply through by T, and we get the following result, that the quantity T, change in entropy of the system, minus del E, since temperature is constant, that's just the variation of the quantity, Ts minus E, must be less than or equal to 0. This is our condition of equilibrium, completely equivalent to del S total less than or equal to 0, but the important thing about it is that it involves only quantities that pertain to the system. There's nothing in the reservoir here, except that the reservoir sets the temperature, but that's the temperature of the system. So I've re-expressed this quantity, this variation, del S total less than or equal to 0, which pertains to the system plus the reservoir, into a condition that pertains to the system only. The difference is that the quantity that appears in brackets is not just the entropy, but Ts minus E. If I multiply this through by negative sign, it's convenient to do so, then I get, if this quantity must be a maximum, the Helmholtz free energy, E minus Ts, must be a minimum. That is, del F would have to be greater than or equal to 0. And we led to the result that if we care about a system in which we control the temperature, the volume, and the chemical content, then the condition of equilibrium which pertains to that system all by itself, forget the reservoir, is that the Helmholtz free energy, E minus Ts, must be a minimum. Expressed mathematically, any change in state must cause the Helmholtz free energy to change in the positive direction for given values of T, V, and N. Well, that's our first alternative thermodynamic potential, and that pertains to a system in which we allow thermal interaction only. Well, now let's suppose a system that really is more common in the laboratory, where we allow both a thermal and a mechanical interaction. And if we're talking about fluids, the mechanical interaction is just pressure and volume. This is a situation in which, in fact, most of the time, if you are doing an experiment on a solid in a laboratory, the temperature will be the temperature of the ambient or the temperature of the furnace in which you put it. The pressure will be the pressure of the ambient. When the body can expand or contract, equilibrate with that pressure. The chemical content, well, if you have a liquid sealed within a container, the chemical content is constant. If you're talking about a solid, ordinarily, just the surface of the solid acts to seal it off, and you can ignore any sublimation of the solid or interaction with the vapor. So a very common laboratory situation, in fact the most common, is where the effective variables that are controlled are the temperature, the pressure, and the chemical content. In other mechanical situations where I, for example, actually impose a high pressure, or it's a little different, but imagine putting this in some sort of pencil machine and pulling on it with a mechanical force. There again, I'm controlling effectively the pressure, the temperature, and the chemical content. So what's the relevant situation there? Once again, let's take our system that we care about. Let's enclose it inside a big system that's a reservoir. The function of this big system, which can just be the ambient in the laboratory, is to fix the pressure and the temperature. So we apply the total, on any change in state of the composite system, the total entropy change must be negative or 0. Once again, that's del S plus del SR. The reservoir changes now include both its thermal interaction with the system and its mechanical interaction. So the change in the entropy of the reservoir is 1 over T, change in the energy of the reservoir, plus P over T, change in the volume of the reservoir. Again, energy and volume are conserved, so del ER is just minus the change in energy of the system. Del VR is minus the change in volume of the system. So I wind up with minus 1 over T del E plus T del V. Well, again, let me multiply through by the temperature. Recognize that both the temperature and pressure are constant. They're fixed by the volume. So I wound up with any change of state which occurs at constant temperature, pressure, and chemical content. The variation of the quantity, Ts minus E minus PV, must be less than or equal to 0. Everything inside this parenthesis pertains to the system alone. I don't need to know what the reservoir is. I don't need to know anything about it in order to apply this condition. except that it sets the temperature and the pressure. Let me multiply through by a negative sign again, because it's always easier to work with minima rather than maximum. And let me define a thing called the Gibbs free energy after J.W. Gibbs. G is E minus Ts plus PV. Then the condition of equilibrium for a system in which I control the temperature, the pressure, and the chemical content is that the Gibbs free energy must be a minimum. That is, the variation of the Gibbs free energy in any change of state in which those quantities are fixed has got to be greater than or equal to 0. This, incidentally, is a source of huge confusion in people. Well, for 40 years, I taught the graduate course in thermodynamics over in material science. And we get people coming from undergraduate from thermodynamics. Most of material science, most people have had a fair amount of thermodynamics as an undergraduate. This I found to be an enormous source of confusion, because over the years they've been told, well, the entropy must be a maximum, and then the next lecture they'd be told the Gibbs free energy must be a minimum, and no one would ever explain to them how these two statements could be consistent with one another. They refer to different experimental situations. If I have an isolated system, the entropy must be a maximum. If the system is not isolated, it's no longer necessary that the entropy be a maximum. The entropy of the system plus its environment must be a maximum, but not the entropy of the system itself. If I have a system in which I control, if the experimental situation is such that these are the variables I control, then the quantity of interest is the Gibbs free energy, and it must be a minimum. So those two statements are not inconsistent in any way. They simply refer to different experimental situations. Since this is a much more common experimental situation, you will ordinarily talk about minimum free energy rather than maximum entropy, because this is the kind of experimental situation in which you usually find yourself. There's another very important one, which is in fact rarely, for some reason, because it's a very useful thermodynamic potential. It is not usually covered in elementary thermodynamics books, but it's quite important, and that is the open system. In virtually any experimental situation, you are often called to deal with systems that are effectively open. You simply take a subpart of whatever system you have, draw an imaginary boundary around it, and you're concerned about what goes on inside that little imaginary boundary in space. Perfectly legitimate thing to do. In that imaginary boundary, you control the volume, because you have to define what you're talking about. So you have to say where the boundary is. That defines the volume. But the temperature is set by the reservoir, and since chemical quantities can go back and forth across that boundary very easily, the chemical potentials are set by the reservoir as well, just by the conditions of internal equilibrium. So the variables I control when I imagine an open system or something enclosed in an imaginary boundary are the temperature, the volume, and the chemical potentials. So let's go through the same mathematics. Take the system, join it with its surroundings, which fits T and U. Take the total entropy, the entropy of the reservoir. Change in the entropy of the reservoir is just 1 over T, change in the energy of the reservoir, minus 1 over T summation over all components, chemical potential of the kth component, the change of its quantity in the reservoir. Since energy and material are conserved, these are just the negatives of the corresponding quantities for the system. So now we're left to, multiplying through by T and U, which are constants, we're left to this quantity right here, Ts minus E plus the summation Un, which must be a maximum. Well, it's again convenient to turn it around and define what's called the work function, which is E minus Ts. We've taken the thermal energy out, if you want, and the chemical energy out. And that has to be equal to, this has to be a maximum. The variation has to be greater than or equal to 0. This is wrong. I'm sorry, there's an error on the slide. I'll fix it. This has to have a maximum value. If I go back to the old integrated form of the energy and plug that in, this turns out to be just minus the product of the pressure and the volume, which is why we call it the work function. Effectively, this thing is just the mechanical energy that's contained in the system. And this tells us that minus PV must have the largest value consistent with given values of temperature, volume, and chemical potential. Since volume is constant and I have a negative here, this tells us that the pressure in the system must have the minimum value that is consistent with given values of its temperature, volume, and chemical potentials. And this is the thermodynamic potential that governs the behavior of an open system. Isolated system, E, V, and N are controlled, the entropy must be a maximum. If there's thermal contact, T, V, and N are controlled, the Helmholtz free energy, E minus Ts, must be a minimum. Thermomechanical contact, T, P, and N are controlled, the Gibbs free energy, E minus Ts plus PV, must be a minimum. And for open contact, T, V, and U are controlled, the work function, minus PV is a minimum, or equivalently, the pressure, P, must be maximum for given values of T and U. I did not write it in, but if you plug in the integrated form for the energy, E is Ts minus PV plus summation Un, the Gibbs free energy turns out to be just the summation chemical potential multiplied by content. It's in the notes. So if you want, the Gibbs free energy is telling you the total chemical energy content of the system. The work function is telling you the mechanical energy content of the system. And those are the alternative chemical potentials. All of these conditions of equilibrium are valid. They are in no way contradictory. They pertain to different experimental situations. And they are very convenient for you, because you can always take the system you're working on, join it with its environment, call it to an isolated system, and apply the second law. But that's unbelievably inconvenient when your reservoir is a furnace or pencil testing machine or something whose inner workings you don't care about. This allows you to focus on the system itself and to phrase the conditions of equilibrium and stability in terms of variables that pertain to the system only. In fact, here, if I just plug in, I'm doing a blackboard if I find a piece of chalk. I should have this on the slide, but the integrated form of the energy, which I asserted but didn't prove, but I can prove it, okay, is Ts minus PV plus the summation over K, UK, in K, okay? Look at that quantity right there. The Gibbs free energy is equal to E minus Ts plus PV. Therefore, it's equal to the summation over the chemical components, UK, in K. So just an easy way to think